Hello everybody, I am Matteo Andreottola, I am a structural engineer. I am of course as well part of Rothoblaas and in particular Roto School. What is Roto School first of all? Roto School is a part of Rothoblaas taking care of the formation of internal people but also external people. So we make courses and seminars every year for people interested in the timber sector basically. We have, for example, this year almost 120 courses around the world internationally in 7 different languages. And we decided as well to do these video lessons. These are for us very important. We'll have 9 video lessons this year, free of charge for everybody, because we think that timber is a great material to work with, has some great potential and characteristics, structural characteristics and also beauty, of course. But it is a material that if you want to use, you have to design in the right way, just to avoid issues of durability, to have the right connections in your buildings, and so on and so forth. So we placed 9 video lessons about the 9 hottest topics we think this year, and let's see how it goes. So first of all, I wanted as well to introduce a little bit what Rothoblaas is. Rothoblaas is a company based in the north of Italy. In fact, I'm speaking to you at the moment from Cortaccia, which is a little town from in between Trento and Bolzano, in the middle of the Dolomites, very close to Lake Garda, if you're not from Italy. So a very beautiful part of Italy. You can see as well from the image here where all of our subsidiaries are located all over the world, because we are actually working all over the world, close to where you are. We have 6 main lines, and these are the screws, for example, screws for wood, the plates, the tools, the soundproofing, the fall protection and safety, the tapes, sealant, and membranes for the airtightness and waterproofing. This is why we have an alpine heart but an international spirit, because we are located right in the middle of the Dolomites, but we are as well present and located all over the world with our subsidiaries. As you can see here, we are more than 400 workers in Rothoblaas at the moment. Actually, we are almost 500 as we speak, because we keep on growing and growing. And if as you can see here, but we're going to discuss more in detail also in the video lessons, also this particular mass timber structure here, we just recently finished the construction of this massive and very nice automatic mass timber warehouse that we have here in our headquarters of Rothoblaas. And this will, and actually has already doubled the existing warehouse space that we have in Rothoblaas. So for us, it's practice what you preach. We preach with our Roto schools around the world to use timber, and also for our own project, we use timber. The use of wood and of timber structure, of course, for us is very important for, as you all know, a sustainability point of view, very, very important. And this is why we preach also the use of this kind of material, structural material in this sense. But of course, as you all know, timber is a material that a lot of people are passionate about, and myself, I'm the first one to be passionate about it. And second of all, it has a lot of very, very good structural characteristics that we'll see throughout the video lessons. And this is why a lot of people love timber, not only because of its beauty, but also because of sustainability and great performance, really. What are these video lessons that we're going to do this year? There are 9 of them, actually. We start with the potential of CLT and mass timber, actually. Then we'll go for durability of timber structure and corrosion resistance for outdoor solutions, waterproofing and airtightness of timber structures, the acoustic in timber constructions, the fire design in timber structures, the seismic design, the composite structure or hybrid structure, a very hot topic nowadays to optimize the use of timber, the innovative connections for timber structures, and last but not least, the installation of full rest system. Thank you very much, and thank you for your attention.
Hello everyone, we're going to talk about durable connections in wooden building. The presentation will focus on corrosion, aggressiveness on different environments where the fasteners are placed. So we're going to go through some of the basics of the selection process, and we're going to go from the most basic concepts to installation and selection prescriptions. So we're going to go through some very important concepts, which are service classes, timber corrosivity class, and atmospheric corrosivity class. Service classes, I think, are one of the most common categorizations that we know for design process. But we want to answer the question, how is the corrosive process influenced by moisture and temperature of the surrounding environment? Concerning timber corrosivity class, which is a more innovative, a newer concept a newer concept, which is a newer concept, we're gonna ask ourselves, how do factors such as equilibrium, moisture content, and wood acidity accelerate the corrosive process? And finally, concerning atmospheric corrosivity class, this is another concept that we should be used to. We will ask ourselves, how does atmospheric aggressiveness influence the connector corrosion? So the conjunction of these three concepts will be the focus of this presentation. To begin, we need to understand that corrosion is a completely natural phenomenon. It is not a matter of if corrosion will happen, but when corrosion will happen, when it gets to any metal, in this case, fasteners. So when we add energy to any mineral to make it to transform it into a metal, in presence of the environment, that metal will tend to become to convert to its initial form, which was the mineral form. So it is a completely natural phenomenon that is triggered by the contact of this element, of this new metal, with the environment. For corrosion to occur, three factors need to be present. I'm not a chemist. I'm not going to go deep into the chemistry of electrochemistry of the process, but you need to know that we need three things in order for corrosion to happen. The first thing, and that is pretty obvious. Sorry, I'm getting back here. That is pretty obvious, is that we're talking. The first thing, and that shall be pretty obvious, is that we are talking about a metallic element. So we need an anodic reaction, which is represented by the metal. A cathodic reaction, which is in many times presented by the oxygen. So we need oxygen to be present. And finally, an electrolyte that will allow the current circulation. And it's generally water. In our cases, in residential cases, and in most of construction cases, it is represented by water. So we need all those three elements. So you can see that we'll be talking about the fastener, so the metal will be always present. Oxygen, it's very rare that it's excluded from the equation. And finally, the electrolyte would be the element that we would be able to play the most with, to play with it in the design, during the design process. There are three concepts within the regulatory those three concepts that we saw earlier are part of the regulatory categorizations, the actual regulatory categorizations, in different norms, and represented also by different parameters, characterized by different parameters. So the service classes are inside of the Eurocode 5, and they are the characteristics parameters that determine the service classes are atmospheric humidity, temperature, and moisture, and exposure time. The atmospheric corrosivity class is presented in the ISO 12944, is an international standard. it depends mostly on zoning, where there is an urban, rural, marine environment, and then the presence of polluting agents, whether it is acid rains, chlorides, etc. Finally, the timber corrosivity classes, which is again the newest concept, is presented by the recently approved 14592, European standard 14592. It depends exclusively on the equilibrium moisture content and acidity. There are other factors also that could affect the timber corrosivity classes, and we're going to take a look at them further into the presentation. So how does these three concepts play together? In a case of a fastener installed in a timber element, these three concepts act in a different part of the connection. So the atmospheric corrosivity class concerns mostly the exterior and the contact of the fastener with the elements in the environment. So as you can see, you will have mostly the exposed head of the screw affected by the atmospheric corrosivity class. A little part of the screw which is in contact with the timber will be also affected, but it is negligible. And it is, as atmospheric corrosivity class depends mostly on the deposition, on the ability of the deposition of polluting agents, such as I said before, acid rain, mostly chlorides in this case. Wood corrosivity classes concern where the element is inside of the timber. So from the tip of the screw in this case to the external part of the wood, where the screw is placed. If it was a plate as well, a plate could be subject also for wood corrosivity classes, and it would concern where the plate touches the timber. So everywhere the fastener, the metal, is in contact with the timber, the wood corrosivity class will affect the corrosivity or the behavior against corrosion of the connection, but no further. Finally, the service class, again the easiest of the concepts, will take into consideration the moisture content. I mean the atmospherical humidity. Take into consideration the moisture content of the wood in the context of that atmospheric humidity, and will put together, it is sort of a bridge between the atmosphere and the wood. But it mostly also concentrates in the parameter of moisture outside and inside of the timber and temperature. When you see the two classes together, you see that there is little to no intersection between those two affection zones. So there is only a small line where wood corrosivity class and atmospheric corrosivity class intertwine. But as I said, the wood corrosivity class ends with the wood, and the atmospheric corrosivity classes also ends when it after, let's say, the wood. Put together, as I said before, are put together the wood corrosivity classes and the atmospheric corrosivity classes. So they are the link, the bridge between them two. The atmospheric corrosivity classes go from a C1 class to a C5 class. They are represented by the letter C, as it is already presented by some years in the ISO standard. The timber class, the newest class, goes from a T1 to a T5 in an analog way of presenting them. T1 being the less aggressive, T5 being the most aggressive. Same for the C class. And finally, service classes. You know, service class 1 to 3, being service class 1 like the driest, and service class 3 the more humid. The newest Eurocode 5 will present a new service class, who will be the service class 4, and will be the maximum of the service classes. As of today, in the Eurocode 5, 3 classes are presented for service class. So class 1 is represented by a 65% humidity, external humidity, atmospheric humidity, which translates to an equilibrium moisture content of 12, which is the humidity inside of the wood. It's normally what you would consider for an interior environment. A service class 2 is would be 85% of atmospheric humidity, equilibrium moisture content inside of the timber of around 18%. It would, as we generally know, it would be an element that is not in an inside, that is in an external, in the exterior, in an outdoor environment, but not exposed to weather conditions. And finally, service class 3 was for elements that were more humid than class 2, where equilibrium moisture content was above 20%, and they were all categorized as wet elements. And this is the current state of the art. This is the current, what the standards currently present. What is coming, the new, what will come in the new Eurocode 5 will be 4 service classes. Mostly service class 1, 2, and 3 would remain as they are now, and service class 4 would be the new one. There are some very well defined limits, threshold limits from one to the other, being you will have one represented by the maximum or the upper limit, and an annual average. So the upper limit from service class 1 to service class 2 would be 12% inside of the timber, 12, 20, and 24. And as you can see, 65% and 85% are the same values as we saw before. We are adding a 95% to determine the threshold, the upper threshold of the service class 3, and service class 4 is for saturated elements. The annual average. This is also a novelty here, that you have an annual average. You can measure, let's say, the service class depending based on the limit or the annual average. So inside of the timber, you have the 10%, 60%, 16%, and 18%, and saturated. You will see also, we will check in the next slides why this is happening and why does this make sense as well. But this is in general the novelty of it. So the service class 1 in terms of exposure will remain generally, or say the most common case will be internal elements. Service class 2 external but covered or protected against weather conditions. Service class 3 external elements unprotected, and service class 4 external elements wet elements that are saturated. The atmospheric corrosivity class classified from C1 to C5, and the classification, the categorization depends on moisture. It's very dependent on moisture. So depending on the presence, water or water vapor is the means is used by the polluting agents to get from one element to the other, to deposit in some elements. So if an environment is drier, the less probable is that polluting agents can deposit in any surface. So the wetter an environment is, also the more aggressive it is in terms of the deposition of polluting agents. The main element to consider from passing classes for the categorization is the exposure to chlorides, so the deposition rate of chlorides. And it will depend, the norm shows a very simplistic way of approaching that. And we're measuring from the further to the closest it is to the coastline. So the further away you are, if you are very far from the coast, you can consider that you are in a C1 class. It would be very rare, though, that the C1 class can be presented, because we're talking about really, really, really far elements from the coastline. C2 can be considered more or less about 10 kilometers from the coastline, more than 10 kilometers from the coastline. From C1 to, from C3 would be considered from 10 to 3 kilometers to the coastline. C4, we're getting higher into the aggressiveness, from 3 to 20 to 100 to from 3 to 250 meters from the coast, from 3 kilometers to 250 meters from the coast, and finally less than 250 meters from the coastline, you will be in a C5 atmosphere. This is very approximative. This is to be used as an indicative parameter, but it gives you an idea of how the concentration changes whether you're closer or further away from the coastline. The other source of chlorides, I mean, this is what's used because the sea is the most common source of chlorides, but another very common source of chlorides is de-icing salts. So if you are very close to the icing salts, so it's main roads, like highways and important roads, you could be between a C3 and a T4 and a C4 environment as well, also depending on how close you are from those sources of chlorides. Finally, exposure to pollutants is it used to be very important in the 80s, 70s, 80s, but policies on emissions have changed and have become very strong. So it is not as important at the moment as the exposure to chlorides. Nonetheless, if it happens that you're in an industrial environment, it could happen that you are the deposition content of SO2 can be important, can be from C3 to T4. So depending on the level of pollution of SO2, you can also change the atmospheric corrosivity class. If you want to go into the detail, you can see here as well that it is measured aside from the distance to the coastline. There is a deposition rate of chlorides, so you can check also on what is the deposition rate specifically of your building. So just to show some examples of what can be considered C1 or C5 category. This is an example of a C1 place. C2 could be also an internal environment, but a very, let's say, a high humidity internal environment like a gym. Also, this is a classical exposed element, but weather but not exposed. C3 environments can be also internal, can be breweries or industrial factories, but with low, not so aggressive pollutants. A C4 environment could be a salt silo or a swimming pool. And finally, C5 environments are elements that are very close to the sea. If you want to go into the details of your city or your construction site, there is the exposure site catalog. I recommend you to look for it into the web. It is a European funded and a European project to map the atmospheric corrosion categories around Europe, and you will find that an overview of many places in Europe. They are mostly research centers and universities. But you can check the corrosion rate on different metals on different parts of Europe. And if you want to go specifics into your place, you might find your city there. This is a growing project, so that you maybe not today, but in some years you will be able as well to check on your city if it's not available at the moment. For example, for Genoa here in Italy, you will find the chart for Genoa. And you can see that the corrosion rate, for example, in zinc, which is the most important for us, as every fastener is coated by a zinc layer, regular fasteners, you will see that the corrosivity category is C3, okay? So it's probably not right in the coastline, but it could be a C3 environment. For aluminum, it is C3. For copper, it is instead C4, okay? So you could have different results from just measuring the distance from the coastline. As you can see here, as for zinc, it is T3. If you go, for example, this is an example of Barcelona as well, which is probably this is the further away from the coastline. And the zinc, for the zinc, it is a C3 corrosive class. So you can check also. I recommend you to look it up. Let's go to the timber corrosivity class. This is as I said before, the newest concept, and this is the way that it will be presented. That it is actually presented in 14592, the EN 4592, the norm for fasteners, and that is also the that will be referenced in the Eurocode 5, the new Eurocode 5 that should be available in 2025. So I said earlier to remember the upper thresholds of the mean. The thresholds on the mean values of the service classes, because they are related very closely to the timber categories. So as you can see, and as I said before, you have 5 categories for timber aggressiveness. They go from T1 to T5. The first and main parameter that affects timber corrosiveness is moisture content, the average moisture content. So every species with moisture content and less than 10% can be considered T1. Every timber species, even if it's treated or not treated, if it is in a service class 1, because this is this is what service class 1 means, you can consider that it is non-aggressive or the least aggressive possible. T2, instead, it goes from 10% to 16%. Again, here, every species, whether it is treated or not treated, regardless of the kind of wood, in these conditions of moisture, can be considered a T2 class, which is a higher level of corrosiveness, but still low. I'm going to T5, so we can also check that box. T5, every timber class that is permanently above 20% of moisture content, internal moisture content, can be considered a T5, which is the highest possible aggressiveness level. So whether it is non-acid or acid or non-treated or treated, if it is above 20%, it is considered very aggressive. Finally, let's get into the details of these 2 classes, which is the T4 and the T3. Okay. There's a division between when you are in between 16% and 20%, a division between the classes, and it is concentrated in the pH. Here is where the acidity, where the species, the kind of species, and the acidity related to the species influences the norm. So there are some species that are more acid than others. The parameter for measuring the acidity is the pH, and that would represent that your species is in the T3 category or in the T4. But remember as well that this range from 16 to 20 is for service class 3 only. Okay. In most cases, if you are in a full indoor environment or in an outdoor but protected environment, you can not do this further analysis, this deep analysis into the species. If you are in service class 3, though, you have to check the species and the acidity of them. So in the T3, you will see that there are most common species, larch, pine, birch in construction, and they have a pH above 4. Less than 4 would be considered T4, and most of them are hardwoods, and they are what we should consider aggressive timber. So it's oak, chestnut, cedar, Douglas fir, and beech. In T4 also fit every example of treatment that adds a substance into the mix. Generally, there are compositions with chlorides or copper and fire retardants. It's very important that you check the kind of treatment that it's been used for for the treatment of the element to check if it will influence the acidity, so it will get into a T4. To simplify and to summarize it, these are the 5 classes from T1 to T5, and the thresholds, the moisture thresholds. If you compare it, this is also what it makes sense also with the new 4 classes, because this is the current Eurocode 5. You will see that the timber class 1 would fit completely into the service class 2. The timber class 2 will fit completely as well, or mostly into the service class 2 as well. But then you will have 3 timber classes, T3, T4, and T5, that will fit. All of them will fill in the service class 3, regardless of the difference in the humidity of them. So the new classes, the upcoming classes, will divide these cases so that T1 will fit as service class 1, T2 will fit service class 2, T5 will fit completely in service class 4, which is an extreme condition so that you can check that when you have service class 4, you will always have a T5 and that's it. That the same goes for T1 and T2. If you have a service class 1, you will always have a T1. The service class 3 will remain the focus point. So when you are in service class 3, you need to be aware that you can have a T3 or a T4. Okay, and it will depend on the pH, so the acidity of the timber and whether the timber is treated. The pH. Let's go inside of the element of the tree. As I said before, it depends on the species, and it varies. So most of the construction species, let's say, fit into the T3 categories. So spruce, European larch, and pine, like Scots pine or Baltic pine, fit in the T3 category. And as you can see, there are many of them also here. So I recommend you to check where the class that you're using fits in the T3 or T4. In T4, you will see many hardwoods. It's not necessarily that every hardwood is a T4, but many are here and in T4. So like oak is a very important, let's say, acid species. Douglas fir, very common in North America, is a T4. And very interesting case, the case of thermally treated woods. So you can see here that, let me just zoom here. You can see that thermally treated beech, it has a 3.4 pH, which is very acid. The limit is 4. But untreated, let me check. Let me go. Untreated beech, which you can find here, has a 5.9. So the thermal treatment has a strong influence into the pH, changes even the pH and the aggressiveness of the element. So be aware that thermal treatments can also affect the acidity and the aggressiveness of these elements, of the trees and the timber. So why does this change make sense apart from of the design? So currently the service classes, this is how the service classes relate to the corrosion rate of zinc, okay, which is the most common coating. Service class 1 goes from 0 to 10. The threshold goes from 0 to 10 moisture content. As you can see here, the corrosion rate is completely 0, so you are completely free of corrosion in service class 1. Service class 3 goes from 20 to 50, let's say up more than 20. And as well here, the corrosion rate goes from 10 above, so you are very sure that in service class 3 corrosion is going to be, there's going to be corrosion and very active corrosion. But in service class 2, you are in a gray area where from 10 to 16 more or less corrosion can and cannot be, and from 16 to 20 where corrosion most cases will be present. So it is a gray area where you are not sure if corrosion can or cannot happen. So this is what is present at the moment. The new corrosion, so just to keep in mind, the corrosive process is triggered when 16% of equilibrium moisture content is exceeded. 16% is right here. This is where the first point is measured. And this graphic can be used as well for to project if you want to design the necessary coating of connectors. If you know that your design, your building is going to be exposed 10, 12 years, you want to know how thick the coating should be for those 12 years, because you are also changing maybe the fasteners. You can design the corrosion, the coating thickness following this graph. Apart from that, this is how the new service classes fit into this chart. So service class 1, same as before. Service class 2 ends in 16%, so that you know in service class 2 the probability of corrosion is very, very low. In service class 3, as we saw before, the probability of corrosion is present, and in service class 4 is high. So the corrosion is present, completely present, and the corrosion rate is very high. And that's why also these four service classes make sense. The norm will prescribe different coating thicknesses for each class. So if you are in service class 1 or in a T1 environment, you can avoid even having coating. From 2 to 4, it will be necessary. In class 2, at least 10 micrometers would be necessary. 10 micrometers of zinc coating, it is the common on the market that you will find for every for screws, timber screws. T3 to T4, you can start having an important coating level. So for T3, you will see that 20 micrometers is necessary, and for T4, 55 micrometers will be required. It is a very, very high, very, very thick element, so it is difficult to produce thick, zinc coatings that will fit this requirement, at least for screws. Stainless steels, so you can also use stainless steels. A T3 can be represented by a CRC2, then T4 and T5 would be necessary at least a CRC3. These are the requirements from the Eurocode 3. You will see that a T3 would be represented mostly by an A2 steel, and the CRC3 that we talked before is an A4, just to give an example of what can fulfill that requirement. This is the chart that you will find in that could have been found. You will see that these are the CRC classes. CRC2, this is the A2, CRC3, A4, and there are also CRC4 and 5, which are higher corrosion resistance, resistant stainless steels. As I told you before that it depends. The corrosion categories depends on the distance to the sea. The corrosion resistance, if we make a correlation between them and the distance to the sea, we can find also which is the coating that we need depending on how close we are to the sea. So there is no zinc coating that could fit the C5 corrosion class. The C4 corrosion class will be very difficult to fit with 110 micrometers. These we're talking back about atmospheric corrosion. From 3 to 250 meters, you will need 110 micrometers. From 10 to 3 kilometers, you will need 55, and above 10, you will need less 2 micrometers, depending on how close and the deposition rate of the chlorides. And concerning stainless steel, we talked about before zinc. This is stainless steel. For the closer than 250 meters, you will need a high corrosion resistant stainless steel. This is the only solution that we have for elements that are very close to the sea. And A4 will start performing well, will start be suitable from 250 meters to the coastline, and A2 from 1 kilometer to the coastline. Putting everything together, placing the requirements of corrosion resistance and timber resistance, this is what a chart would look like of the corrosion resistance of the different coatings, if we are talking about zinc-based coating or the stainless steel. So, for example, if we're talking about a regular standard wood zinc-plated screw, you would fit into this class. So that standard screw would be a C2 T2, so it can resist that corrosive atmospheric class 2 and an atmosphere of class 2 and a timber environment of class 2. A hot dip could resist an atmosphere of 3 and a timber of 4. Our coating C4 Evo, an alternative coating, would resist an atmosphere of 4, class 4, and a timber class 3. This is very important. For resisting a 4-4 class, 4-4 condition, you would need a hot dip of 110 micrometers. Then for stainless steels, you can do also the same game. A2 will resist a 3-3, A4 will go 4 and 5, and HCR, the most resistant, high corrosion resistant, will go 5 and 5. So we had a look at the base material, at the coating type. These are the requirements for the connectors. Then we also placed together the wood species and the corrosivity class of the environment, and that would allow us to do a corrosion assessment that we can use in the design to check if we did a correct design selection, at least. So, but we need to ask ourselves as well if there is the connector in a safe condition. So there are, for this assessment, the most important parameters to consider are right here. So we saw how the equilibrium moisture content affects the aggressiveness of the classes, whether it is the atmosphere or the timber. The pH and inside of the timber, we also checked how the pH, so the acidity of the timber affects the corrosion. Point 4 polluting agents, chlorides, mostly determine the atmospheric corrosion class, and also we saw that. So we are left with two points that are important as well: tannins and galvanic coupling. Let's take a look at the first, tannins. So we did an experimental test, and obviously an experimental campaign, to check the effect on tannins. This was very based on the experience that Samuel Zelinka had already had. So we placed one of our screws for these were from 2 to 6 months in green oak, service class 3, in an atmospheric corrosivity class C2, which is the Rothoblaas headquarters. Outside of Rothoblaas headquarters, we're in a C2 class, and the wood corrosivity class being a green oak, it is T4. So what happened to this screw? In the exterior, you will see no corrosion because it was a C2 atmospheric corrosion class. So in that period of time, no corrosion happened. Inside of the wood, you will see a black coating. Let's call it black coating. But you won't see rust. You won't see red rust or white rust. You will see a black surface. And so you would deduce it is low corrosion. But in the first centimeters below the surface, you will see the red rust. That is strong corrosion. So what happens is that the tannins creates a protective layer. I mean, they attach to the surface of the fastener and create a protective layer that will increase the resistance, the corrosion resistance of fasteners. But in this area, in the area with the number 2, is the area where water can wash down tannins. When it rains, water can penetrate more or less until the white dots, washing the tannins and then allowing for corrosion to increase. So this experience was also demonstrated by this is more or less an example of what the setup was also demonstrated by Samuel Zelinka. As I said before, this our experiment departed from his research. So if you take a look at this graph it is a graph of corrosion rate in wood extracts depending on pH and tannin content. So these lines are the corrosion rate. So you have corrosion rate of 50, 75, 100, etc. The pH is in the y-axis and the tannin content in the x-axis. So if we take a look at these two elements, which are pine species and an oak species, with a very similar pH, you will see that the corrosion rate is different. So the oak has a corrosion rate about 350 because it has a very high tannin content, around 1,000 milligrams per liter, while pine has a corrosion rate of 450 micrometers per year, more or less. And the thing here, the clue here is that the tannin content of pine is a lot less, determining that the corrosion rate is higher in this case. The conclusion with tannins is that they are not a catalyzer or an accelerator of corrosion, but a retardant, a corrosion retardant. It's very important to say that nonetheless, tannins, the pH is the most determining factor of for the acidity or for the of the speed of the corrosion process. So to conclude with this assessment, there's the selection and the atmospheres assessment. You need to check the service class where the metal is in, the timber or the wood element where it is, and the also the atmosphere or where it is. So these three environments play a role together. The atmosphere and the service class will give you the atmospheric corrosivity class, and the wood and the service class will give you the timber corrosivity class. The combination of each factors give you one of those elements. So if you chose the right metal to fit those factors, you can also say that the fasteners in a safe condition. But it is still necessary to check if the design was correct. But because even if you choose the right fastener that would fit all of those categories, it is not yet finished. The assessment is not yet finished. So another thing that can happen, and as the other concept that we left out in the list, is galvanic coupling. So many times you are not only joining timber elements with the fasteners, but you're also joining plates with timber using a fastener. So three elements need to be present in order for galvanic coupling to happen or to be an issue at all. So if one of these elements is not present, you can be sure that galvanic coupling does not happen. So the first thing is that we have different metals. So elements, metals with different electric potential. So you will have a plate, for example, which is zinc, which is a carbon steel plate with an electroplated coating, a zinc electroplated coating, and a screw, which is an A4, a stainless steel screw. These are elements with different electric potential. We'll see that also in another slide. The presence of an electrolyte. So we're talking again here, service class 2, service class 3, service class 4 even, not service class 1. So if the electrolyte is not present, then this won't happen. Finally, direct contact between the metals. So electric continuity between the metals. And you would say this is obvious, but you will check that this can also be avoided and prevented some ways. So what do we mean with different potential? So in a galvanic series, you see what different metals behave differently, and they work in different potential. There is a range of most noble to least noble. Okay. Okay, so what do we mean with galvanic, with difference in the potential? So in a chart, if in a galvanic series, you will see that the metals are placed with different voltage, with different potential, going from the most noble to and thus the cathodic, the one that will tend to lose metal, that would corrode, to the least noble, the anodic, or the one that will not corrode. So in this chart, the further away one metal it is from the other, the highest thus is the potential, and the highest also is the corrosion rate. So in this case, you see that stainless steel, this is 360 stainless steel, will fit more or less here. This is the voltage in this of the stainless steel. Compared to the zinc, there's a lot of difference, and thus the corrosion can happen. The corrosion will happen. So if we were talking about, for example, zinc and aluminum alloys being very close, the difference in potential is very small, and thus the corrosion would be really, really slow, so slow that it can be considered in many cases as negligible. What can you do to prevent corrosion galvanic coupling? So disconnecting, the first thing that you can do is disconnecting the electrical joint between metals. You will be going to the third principle, which is the direct contact. Placing an element like this is an EPDM washer between them can prevent the galvanic coupling from happening. So you will see that you can have a zinc electroplated fastener with a stainless steel plate, and it would be avoiding the contact between them. You will avoid then the circuit to start and then the corrosion to happen. You can use similar metals with little difference of potential. I told you also before, in the galvanic series, if they are close to one another, for example, zinc and aluminum alloys can be placed can be used one to the other with the other, and they are very little difference of potential, and that can work, depending also on the alloy, the kind of alloy. You can coat either the anode or the cathode to prevent electrical connection. In this case, we're talking about two elements that have been coating with the same coating or a very similar coating, so that the connection there is no difference in the elements that are making a circuit. So there will be no electrical circuit, and the plate here can be aluminum, can be stainless steel, can be zinc. So regardless of what the plate, the material, internal material of the plate, the coating will prevent the galvanic coupling in this case. And finally, you can control moisture from connecting the two metals. It is a similar principle to the one before. You can do it with a band, with a tape or a membrane, any layer that can disconnect the two elements. In this case, this is like a butyl band or a butyl tape. Placing it right. Let me zoom here. Placing it in between the metals, preventing any contact from happening, will also prevent galvanic coupling there. Finally, in some cases, you just can't avoid having the similar metals. In some cases, it is necessary to do it. What we will recommend is to every time place the most noble element, so to guarantee that the screw or the fastener or the dowel type fastener is the most noble element, because in that way the corrosion will affect. I mean, the element that would corrode will be the plate, And the plate being much more, the surface of the plate being much higher, the corrosion will be a lot slower. In that case, then you will see that corrosion in the plate will start, but it will take years. It will take a lot of time to corrode the entire surface. The contrary, if the most noble element is the plate, then the corroded part will be the screw, and then it is also a problem because if a screw fails, then you have a strong structural problem as well, and it will happen a lot quicker. So we will always recommend this first case here if you cannot avoid galvanic coupling. Concerning design as well, is apart from the selection of the metals, you will be required also to prevent water stagnation. For the most, water stagnation will increase. It will not only affect the durability of the wood, as you can see here. You do see here as well the growth of fungi, but also it would increase the moisture content inside of the elements. It would then change the acidity. The aggressiveness of the timber, and then thus it will corrode also the fasteners inside of it. Working into the construction details to allow water to drain, to allow to favor the drainage, will not only prevent the wood material to rot or the decay of the wooden material, but also will prevent the corrosion of the fasteners. So thinking of the connector and the wood as a unique system will allow for a better durability of the joint, the entire joint. The timber also behaves differently in time, and in the forms. It has deformations different in time. So also here allowing for a draining design that favors the drainage would favor also the connectors as well. If you place the elements by reading the structure of the tables, of the boards, of every kind of joint, if they are going to be exposed at the elements, you will also favor corrosion depending on the choice of the formation of the boards. An important thing would be to avoid exposure of the extremity of the wooden element, as it is the place where the wooden elements absorb the most of water, and then thus it will affect the fasteners. And prevent, this is also related to the one before, prevent the transport of water by capillarity, not only exposing them, but also even if they are not exposed, in cases like this where they are connected or in direct contact with moisture, water can penetrate and can travel a lot inside of the element, and that will not only affect the timber, but also the fasteners inside. Finally, just to finish my presentation, I would like to show you an experimental campaign that we did with several of our screws. We wanted to test the different materials that we have in our product range, the coatings, and how they behave in different environments, especially concerning timber environments, so the timber acid T4 environment. So we tested a lot of different screws in oak. As we saw before, oak is a T4 wood corrosivity class. In service class 3, so outside here, in C2, in a C2 environment, so the atmospheric environment was not aggressive. We placed them, and we placed like 12 samples of each kind of coating that we wanted to check, and each month we would go with a chainsaw and take out those 12 samples per month to check it, and that was to avoid the influence of you say, well, we didn't just screw it out. We wanted to avoid the damage of screwing the screw out. So we cut it, and this is one of the main results of so far. There are many other things that are currently being checked, and that will be presented in a different format. But this is one of the most interesting. So 1 month, you will see that after 1 month, the zinc electroplated or the organic coating, C4 Evo, or This is an stainless steel, martensitic stainless steel, AC410. All of them behave really well. You will see that you will see that a little bit of tannins here already attaching to the surface of the zinc electroplated, but as we saw before, that is not rust. So after 1 month, everything is okay with every coating and every material of them. After 10 months, then the differences start to become a lot present. So zinc electroplated, there is a strong presence of tannins, but you will see a lot of red rust. So it's generalized corrosion, critical condition in the entire screw. The organic coating behaved really well. You will see that there's some stains of tannins, but the red rust is also negligible here. So it was a very surprising result here, very promising. C4, it is a zinc-based coating, so we also knew that it would have a performance better than the zinc electroplated, but still there are some minor marks of red rust, a lot of tannins. So we know the C4 Evo for a service life duration, it would not be suitable. Finally, one of the most surprising results was the IC410, which is not yet considered in the martensitic is not considered in the European norm, the 14592, but it was completely rustless, no tannins. It was completely okay. So I think this is a very interesting result also for you to take into consideration. There are some other things that we're checking. We're checking different materials, different positions of the timber. There are many variables. This is what you can see here as a service class 3 and service class 2. Checking what happens if you block the entrance of water in the surface with like a butylic adhesive. What happens if you pre-drill or no pre-drill? What's the difference between exposing them on the surface, on the horizontally or vertically as well, because of the position, in terms of the position of the pollutants, but also if water travels differently inside of the element. The head shapes, head sizes, the distance to the extremity here, different coatings in different elements. So there's a lot going on in the corrosion research. Here we're checking as well, what if you seal the joints, what if you seal the head, what would happen there, will affect it positively or negatively. What if you seal them with a tape, a regular tape? So just that they can be prescriptions and provisions that you could do to make it perform better to corrosion, or maybe the result is that, as it had happened with a lot of them, is that it performs worse. In many cases, it blocks the moisture going out, and then so you will have a wetter element. But these results will be presented in a further presentation. So to conclude, I will conclude with a very simple phrase. If the wood is designed for longevity, so will be the connector. So think about the wood and the preservation of the timber and the preservation of the fastener as a unique concept that would take into consideration both of them. Thank you very much.